Hello everyone. I am Teacher Chen from the Electronic Information Engineering Teaching and Research section of Wuzhou University, and welcome you to this mini lecture. Today we will study section 7.4 in chapter 7 on complex frequency domain analysis of systems. Complex frequency domain, Z-domain, solutions of difference equations for discrete time LTI systems. In the previous sections, we studied the mathematical model of discrete time, linear time invariant systems, constant coefficient difference equations. From the time domain perspective, we have used the iterative method, the classical method, and the convolution method to solve difference equations. Using the iterative method to solve a difference equation has a clear logical process, is convenient for writing computer programs, and can yield numerical solutions to the equation. But it is not easy to obtain a closed-form analytical solution. Using the classical method to analyze the system response is a purely mathematical approach and cannot highlight the physical concepts of the system response. Therefore, just as with continuous time LTI systems, the complete response of a discrete time LTI system can be regarded as the superposition of the responses produced separately by the initial conditions and by the input excitation. That is, the complete response equals the zero input response plus the zero state response. In this lesson, we will learn to use the complex frequency domain, that is the Z-domain method, to solve difference equations for discrete time LTI systems. Z-domain analysis of the response of a discrete time LTI system uses the one-sided Z-transform to convert the time domain difference equation describing the system into an algebraic equation in the Z-domain. The Z-domain expression is then simplified and manipulated algebraically to obtain the Z-domain response y of z, and the inverse Z-transform is applied to find the time domain sequence of the system response. A typical second-order constant coefficient difference equation can be written as y of k plus a1 y of k minus 1 plus a2 y of k minus 2 equals b0 f of k plus b1 f of k minus 1. On the left-hand side, y of k denotes the system output. On the right-hand side, f of k denotes the system input. The system has initial conditions y of minus 1 and y of minus 2. Step 1 in solving the difference equation. Take the one-sided Z-transform of the above difference equation. First, apply the time shift property for the output. Because the system has memory, it can store some initial values. When the circuit switch closes and operation begins, these initial values produce the zero input response. Therefore, its Z-transform uses the one-sided Z-transform formula for right-shifted sequences, which requires including the initial values when performing the Z-transform. Y of k maps to capital Y of z. Y of k minus 1 maps to z to the power minus 1 times capital Y of z, plus y of minus 1. Y of k minus 2 maps to z to the power minus 2 times capital Y of z, plus y of minus 1 times z to the power minus 1, plus y of minus 2. The input signal is causal and enters the system only at time 0. It has no stored initial values. Therefore, the one-sided Z-transform formulas for the input and output are different, and the input does not require inclusion of initial conditions. That is, the Z-transform of f of k is f of z. The Z-transform of f of k minus 1 is z to the power of negative 1 times f of z. From this, we obtain the Z-transform of the difference equation as shown in the formula. Step 2 in solving the difference equation. Rearrange the polynomials. Place the y of z term to be solved for on the left-hand side of the equation, and move all other polynomial terms to the right-hand side. Simplify the polynomials. After rearrangement, the first term is the Z-domain expression of the zero input response yx of z, and the second term is the Z-domain expression of the zero state response yf of z. Step 3 in solving the difference equation. Take the inverse Z-transform of the algebraic equation to obtain the expression for the output y of k. Next, Let us look at example 1. The system's difference equation is y of k minus 4 times y of k minus 1 plus 4 times y of k minus 2 equals 4 times f of k. The input is f of k equals open parenthesis minus 3 close parenthesis to the power k times u of k. With initial conditions, y of minus 1 equals 0 and y of minus 2 equals 2. Find the zero input response yx of k, the zero state response yf of k, and the complete response y of k. First, take the one-sided z transform of both sides of the above difference equation. On the left-hand side, 1. The z transform of y of k is y of z. 2. The z transform of y of k minus 1 is z to the power minus 1 times capital Y of z plus y of minus 1. 3. The z transform of y of k minus 2 is z to the power minus 2 times capital Y of z plus y of minus 1 times z to the power minus 1 plus y of minus 2. Note that the second and third terms also have coefficients in front of them. Do not omit these. On the right-hand side, the input is 4f of z. After further simplification and manipulation, we obtain the z-domain expression of the zero input response yx of z, the z-domain expression of the zero state response yf of z, and the z-domain expression of the complete response y of z. Substituting the known initial conditions and simplifying gives yx of z. Next, take the one-sided z transform of the input sequence to obtain x of z equals 1 divided by 1 plus 3 times z to the power minus 1. Substitute into yf of z and simplify to get yf of z equals 4 divided by 1 plus 3 times z to the power minus 1 times 1 minus 2 times z to the power minus 1 to the power 2. Then expand yf of z into partial fractions. Then, take the inverse z transform of yf of z and yx of z separately to find the system's zero state response and zero input response. Adding yx of k and yf of k yields the complete response. Finally, please reflect on today's lesson and complete the following exercises, which are designed to consolidate the knowledge points learned today and further deepen your understanding. This concludes today's class. See you in the next lesson.